All right, well, yeah, thanks for the organizers for inviting me to come here and give this talk. So I'm going to be talking about some work I did last year with a student, Jeremy Gagnon-Bischoff, Phil Landry, and Nestor Ortiz. And it's about tides of neutron stars. So I'll explain what I mean by extended I-love relations as I go along. So as I'm sure everybody knows, we've now detected gravitational wave signals both from binary black holes and from binary neutron stars. And there's a big difference between these, of course, which is that binary black holes are vacuum solutions to the Einstein equation. So we know exactly what equations we're trying to solve. But binary neutron stars have a non-zero stress energy, and there's some uncertainty about what exactly are the properties of this stress energy. So, because they have extremely high density, and we don't understand the nuclear physics at these densities. So, in addition to what we try to do with the binary black holes, which is, deduce the parameters of the binary itself, with neutron stars, one tries to actually learn about the physics of this high density matter. Now, there's some other properties that differ between black holes and neutron stars. One is, what we observe with the neutron stars, in addition, because of all this high density matter, we get this multi-messenger astronomy, and we can see light signals and so on, like a gamma ray burst or a kilonova, and try to learn all kinds of things that way. But we can also, of course, look at the gravitational waveform. And the gravitational waveforms of the binary neutron stars and the binary black holes differ in that the binary neutron stars have much longer waveforms, so you can try to extract more information. So, I mean, the previous talk was all about binary neutron star mergers, so I don't need to go over much of this. We have the in spiral, and then they have the merger, and then there's this post-merger waveform. And at the same time, there's all kinds of matter interactions happening, and that can be observed with telescopes. What I'm going to focus on here in this talk is the pre-merger behavior, this in spiral, and we're going to try to see what we can deduce about the neutron star matter by looking at that in spiral. So the typical way that one treats this uncertain nuclear physics is to say the stress energy tensor is just a barotropic perfect fluid. So it has an equation of state, which is the pressure as a function of the energy density. But there are various models of this equation of state, and the game is we try to distinguish them by comparing the signals. So this equation of state, one thing that it imprints itself on is the mass. It just reflected directly in the mass to radius relationship for neutron stars. But another place where it manifests is in the tidal deformability of the neutron star. So so if you have one neutron star, it deforms the other one, and then this is then reflected in the gravitational wave signal. So the idea here is we have some varying gravitational field, which we'll describe by the Weil tensor. So this is just, imagine putting some neutron star in some vacuum region of space-time, and then that causes a deformation of the star. Now, these tides, of course, are well known from Newtonian gravity because we see them on the Earth. And what you do to describe them is you can expand your Newtonian field in a Taylor series about the origin. So we have this leading part of the Taylor series, that's the Newtonian potential. And if this body is sitting in some sort of region with a varying gravitational field, we have this applied tide, which is described by this 1 here times this quadratic part in the Taylor series. This is a quadrupolar tensor, this EAB, and then we get a tidal response. So you embed it in this field, then it creates this additional field far away because that matter deformed. But that tidal response characterized by this coefficient here, which is this K2, and that's called the love number. And that depends on the internal structure of your body. So if we then take these bodies and we put them, we take two of them in a binary, the field of one of these is going to create a changing gravitational field over here at the other one, and that's going to deform that star, so that you get that each star is deforming the other one, and then you get a transfer of energy into these stellar tide degrees of freedom, which then alters the orbital dynamics. And since these orbital dynamics are changing, you get a different time-dependent quadrupole, which then gives you a change in how much gravitational radiation is emitted and different decay rate of the binary. So the result then, going back to Flanagan and Hinderer, is that you get an orbital phase shift during the in-spiral phase, and that depends on this love number. So if you can measure this orbital phase shift, you can learn about what the equation of state is. So LIGO and Virgo did this they looked at this effect, the leading effect, to constrain the nuclear equation of state. So this is some of their results taken from their paper, and what we're plotting here are the tidal deformabilities, basically the love numbers of the two stars, and we have these curves here represent possible equation of states. And what it's saying is these more compact stars, or these equations of state over here, are more favored compared to these ones over here. And that's just from not observing much of a phase shift. There's two figures because they depend on different assumptions on the neutron star spins. Yeah, please ask me any questions also if anything's not clear. Now, looking at these tidal deformabilities, there's this interesting property noticed by Yagi and Yunus in 2013, which is that there are these relationships that are equation of state independent between that love number, as well as the moment of inertia and the spin-induced quadrupole moment of the star. So what they're plotting here are, well, here they're plotting the moment of inertia, suitably renormalized, against the tidal love number, and all these different, it's not very clear, but all these different markers on here correspond to stars with different equations of state, or different stars with different equations of state, and they find that they lie along these curves to just a couple percent level. So there's no real explanation of why this is happening, but it seems to be the case. So this is the moment of inertia versus the love number, and we have a similar relationship between the spin-induced quadrupole moment and the love number. So it's not clear why these hold, and the other peculiar thing is that, well, you get, so here this curve represents neutron stars, but this curve over here represents quark stars. So there's different models for quark stars, and they all have their own universal relation between them. But these relations, however, I don't know exactly why they exist, but they're particularly useful in gravitational wave astronomy, because they tell you that you have these quantities that you could potentially independently measure, and you can then go back and check that they satisfy this relationship you expect. And then that way you can test general relativity, or you could also use that to, if you had some degeneracies between some of these parameters that you're trying to measure, you could break those degeneracies because you have a relationship between them. And also it can help with parameter estimation if you build in these models so that you don't have to try to measure all these independent parameters. You just build in an assumption. So yeah, so this is this I love Q universality. Now, that previous discussion is somewhat limited because real neutron stars are expected to have rotation. And that means, well, they have this rotation, and that's not taken into account. And there's a whole series of papers by Landry and Poisson, and also Pani, Gualtieri, and Ferrari, where they've tried to incorporate this rotation into these models. And what they find is that when you have spinning neutron stars and you have tides, then you have a whole set of additional rotational-tidal love numbers that say how the coupled spin and the tide induces another deformation of the star. And that's something else that you can try to measure. But it's not clear how these new rotational-tidal love numbers might fit into universality relations, whether or not they continue to hold. And in fact, there was some work by Pani, Gualtieri, and Ferrari that actually suggested a violation of them. So the goal of this work is to compute these rotational-tidal love numbers for realistic neutron stars and just check to see if these, well, I'm going to show that these extended universality relations in fact hold. And yeah, that's what we're going to talk about. So basically the outline of the remainder of the talk is I'm going to explain the approach to do this, and as well, and the framework that we're going to calculate all of these quantities in, and then I'll calculate the love numbers and show that the universality relations hold. So the idea here is we want to generalize this Newtonian picture of tides to the general relativistic case. So let's just forget about the neutron star itself and ask how we can describe the tidal environment. So we imagine there's a neutron star that's going to be going along this world line, but just ignore it for now. You can then expand the metric at this as, well, the flat metric. You just expand in this Taylor series. So the leading correction to that would be quadratic in x. It's the Weyl tensor times x squared. And then you get another correction, which is the gradient of the Weyl tensor times x cubed, and so on. So this is the quadrupole, the octupole, the hexadecapole corrections to the metric. Now we imagine, of course, that these quantities are going to be, you know, they're going to exist because there's some external matter distribution that's causing them. But then we take each of these coefficients, each of these c's and the derivatives, and they can be decomposed with respect to the tangent vector, the forward velocity of the star that we've taken away. And then that gives rise to a decomposition into the electric and the gravitoelectric and the gravitomagnetic parts of the Weyl tensor. And these have an L index. That's just a symmetric. It just denotes that there's a certain number of symmetric trace-free indices on this. So we split into the electric and magnetic parts, and that characterizes the tidal environment. So yeah, that's what I just said. And we assume them to be sourced by some external stress energy distribution. So we have this out here. There's some distribution of stress energy. It creates this environment. And now, to understand the tidal response, we're going to put the star back in there. And we assume, for this work, we can assume that the tides that linearly perturb it are static. And that will be a reasonable assumption for the binary, provided that it's a significantly large enough distance between the stars. And we're going to find a corrected solution that incorporates both the star and the tidal environment that interpolates between the two. So the idea is that for each of these multipole moments, each of the electric and magnetic multipole moments, you induce a response that's proportional to a love number. So before we had, in Newtonian gravity, we had the K2L, the response due to a quadrupolar applied Newtonian field. But now in general relativity, we have these higher multipoles, and we also have these gravitomagnetic love numbers, because you can have gravitomagnetism is present in general relativity, but not Newtonian gravity. For this work, we're going to restrict, in fact, to the quadrupolar tides, to keep it reasonably simple, and also because the higher orders are going to be smaller in amplitude. Okay, so that's the story for tides. But now what do you do with the spinning star? So we take that star and we allow it to spin slowly with frequency omega, or angular velocity omega a. And this is going to give rise to multipole mixing. So if you have an interaction between an L-pole applied tide and a dipole spin, that's going to generate responses of multipole order L minus 1, L, L plus 1, and so on. Well, in fact, just those. So for example, if you have a quadrupolar applied tide, like we're used to considering, and we have a dipole spin, that generates a dipole, a quadrupole, and an octupole response. Now, in fact, for the quadrupole, it's a bit simpler than that because this dipole just corresponds to an overall acceleration. This quadrupole induced corresponds to an overall rotation, but the physically important one is the octupole. And the and that octupole, then you have two new love numbers. You have a gravitoelectric one, which is denoted FO, and a gravitomagnetic one, which is denoted KO. So the O here means octupole. And so the complete response to the quadrupolar tides is characterized by the four parameters K2L, K2mag, FO, and KO. So all this was worked out by Landry and Poisson and Pani, Gualtieri, and Ferrari. So, yeah.
Can you go back and explain why the overall rotation can be factored out?
It's just well, I think it's just a change in coordinates. So we could have gone to a different coordinate system at the beginning, and then just not worried about it. I mean, there's a bit of a freedom. It's like a gauge freedom. In a binary, I guess that's a more complicated question to think about that. Yeah, I have to get back to you on that one. I don't have a good answer, but we're looking at the response to a single at a single star. But anyway, just a word on notation, which is that I've written these love numbers here with these small letters. These are what we call love numbers. They're nice because they're finite in the zero compactness limit, and they correspond to the original love numbers as they were originally defined. But it's also very useful to use these rescaled love numbers that I'm just going to denote with the capital letters, because these are the ones that are relevant for the universality relation. And they're just rescaled by powers of the compactness. So just don't be alarmed if I switch between these all over the place.
What is the definition of this second, two second love number?
These?
Yes.
What are the definitions right here?
No, definition of the this is a Gothic
FO?
Gothic S.
Yeah. Oh, these?
Electric,
Yeah, this is the rotational-tidal love number that describes the coupling between the quadrupolar applied tide and the spin of the star, and at the octupole level. Yeah, so it's this one. So you have the quadrupole applied tide times the dipole spin generates an octupole deformation. The deformation in the gravitoelectric sector is this FO. And then the deformation in the gravitomagnetic sector is the KO, the Gothic letters. Is that clear? Okay. Yeah, so I mean, I'll get to the definitions. We'll see how they come out. But so that's the game. We want to calculate these things. Okay. So this framework, just in a bit more detail that Landry and Poisson used is, well, we're going to imagine we have general relativity in a perfect fluid. So we have the Einstein equation with the stress energy tensor. And we assume some barotropic equation of state that depends on the underlying nuclear physics model. And we're assuming stationary quadrupolar tides. And like I said, this is a good assumption as long as the timescale of within the star is much faster than the timescale of the binary, which works at large separations. Now, at the background level, we're just going to have a static spherically symmetric star. So we can write our metric ansatz in this form where we have two free functions of r, the psi of r and the m of r. And later we're going to add in the spin. So remember, we're taking static spherically symmetric at the beginning. And spin will be added later as a rigid rotation. So this only applies for small spins. So if we have our static background, we're going to perturb it. Well, the Einstein equation then reduces the TOV equations These are ordinary differential equations for psi of r and m of r and the pressure. And if you solve these subject to an equation of state, then you get your stellar solution. So outside the star, well, it's just vacuum, so the solution is Schwarzschild. Inside the star, it depends on the equation of state, and the boundary conditions that we have to impose are that at r equals 0, the origin, we require regularity, and at r equals capital R, the surface of the star, we have to match it to the exterior. So this is all very standard textbook stuff on how to study stars. But now we perturb it. So the idea is that we add terms to the background metric that correspond to the applied tidal field and the rotation. And then we're going to allow for radial dependence to interpolate between the star and the tidal environment. So the way to do that is we take all our tidal moments, EAB and BAB, and our rotational moment, omega A, and we treat these as perturbations. And with these, we also have these bilinear moments. So we just combine them in whatever ways we can and add these moments. So we have our moment, we call it FA, which is the tidal quadrupole moment times the rotational moment, and that is then, well, that gives you then a dipole perturbation, and it has a certain parity, this odd parity, and it comes in a particular multipole order. So this is what I just said at the beginning. We generate dipole, quadrupole, and octupole bilinear moments, and we decompose them with respect to parity. We then repackage them again into what we call these potentials that before we put them into the metric on such. So we take these moments and we dot them into radial vectors, and we take duals of them, and this is just needed in order to write down our metric ansatz. So with these potentials, all these terms here, they describe the applied tides and the spins. We multiply them by these functions of r, and we put them into the various metric components. And we do this in such a way that it transforms suitably under the parity and rotation. So we can see in the GTT component, we have the background part, which is just the Newtonian potential, and then we have the electric quadrupole part times, that's that EQ, that's this potential, times this unknown radial function of r. And this is kind of ugly looking, but this form is useful because it means that afterwards the perturbed Einstein equation is going to decouple suitably into these different sectors, and we'll be able to solve for all the functions of r. So notice, though, I said everything was a function of r, but if you look carefully, some of them actually have functions of t in them. And that is because, in fact, you can't get a consistent solution if everything is just a function of r. So even though the applied tides are stationary, this time dependence arises due to gravitomagnetic induction inside the rotating star. So you just this combination of this gravitomagnetic field and the spin. But you can show you can get a solution if you assume that time dependence is just linear in t. And essentially this corresponds to a driven zero frequency stellar oscillation mode. And the fact that we get this linear in t growth, that may look like a problem at first glance, but it's likely just an artifact of this perturbative expansion. And physically, you would expect it to be bounded. Now, that we've been talking about the metric so far, but the fluid ansatz is also necessary. So we need to treat the stellar interior. So we want to decompose all of the fluid variables, just like the metric ones, into tidal, rotational, tidal, and bilinear potentials. But it turns out we can write all of them in terms of the metric perturbations. And the reason, so long as we just assume basically that the star has none of its own oscillation modes excited. In that case, you'll have that the stress energy is entirely determined by the metric. So this the way to see this is, well, stress energy conservation implies that the vorticity is conserved along world lines. And then if you take a variation of that, that tells you that the Lie derivative along the world line of the Lagrangian displacement of omega vanishes. And then, well, then if we assume also that the star began in an unperturbed state in the distant past and the tidal field is switched on adiabatically, then that assumes, then that says that this delta omega had to be 0 initially, but then because of the fact that it's conserved, we can assume the delta omega is 0 for all time. And then if we also assume that we don't have any zero frequency modes and we impose the Einstein equation, then this condition enough is to this what we call this well, this condition itself is enough to just express the metric, I mean the fluid entirely in terms of the metric variables. When we do that, the fluid takes this kind of ugly form. So we have the mu, the p, the ur, and the ua, all expressed in terms of these same quantities, these ETTQs and so on of the metric. We can then, just plug that into the Einstein equation, and then we get the second order ordinary differential equations for all of the radial functions. So this is, all that messy stuff, it reduces to the fact that we can just solve these second order ODEs. And well, when you have a second order ODE, it means you're going to have two independent solutions, and one of them is growing and one of them is decaying at large r is what you find. So this growing solution, that's what corresponds to the applied tidal field, and the decaying solution is the one that corresponds to the tidal response. Now, well, that's just what I said. So if we solve the equation subject to that it matches the tidal environment and that we have regular solutions to r equals 0, that then fixes the solution. It fixes a unique solution, and well, then we can just extract the Love number by looking at the coefficient of the decaying part.
So why wouldn't the correct solution be one that is well behaved at 0 and also at infinity?
Because
rather
then,
than growing.
Yeah, because that's
would be a combination of growing those two solutions.
Yeah, so that the reason is you're asking why do we want it growing at infinity? That's the tidal, that's the applied field, right? So if you do that Taylor series that I mentioned at the beginning,
the star gets ripped apart.
Well, it doesn't get ripped apart, but it's just you're Taylor expanding your field. Yeah, so you get these. It's not, you don't take that literally that you have it completely blowing up far away, but at least in the neighborhood of the star, that makes sense because it's just your Taylor expansion. So we're matching it to the Taylor expansion in that way. But it's a good question. It's basically this matched asymptotic expansion that we're doing. Yeah, so you do get this blowing up part, but I wouldn't take it seriously except that that's the applied tidal field, and you could compute that for any sort of external environment. Anyway, so that decaying solution though, that's the induced field. So in practice, what you do is you split the problem into the interior and exterior parts, and you match the stellar surface. So the exterior solutions are known analytically. They're not. They're kind of ugly, and they didn't even show up very well at this resolution. But all you need to know is that you have basically. So for all these radial functions, there are these coefficients that are undetermined in the radial in these external solutions, and those are our 4 Love numbers, and so the x here in all these functions, that's just r over 2m. And then we numerically solve the interior part depending on the equation of state, and then we get the 4 Love numbers and the moment of inertia. Okay, so yeah, so what we've done is we've taken our static star, we've perturbed it with some rotation and with the applied fields, and then we've worked everything to linear order in the rotation, and linear order in the applied fields, and bilinear order in the applied fields and the rotation. So this is the metric we have in the end, or at least part of it. Well, it's useful, I think, to just look at this. So in the GTT component, we have the Newtonian potential. In the GTA component, we have a rotation term. This is just basically linearized Kerr metric. We have an acceleration due to the spin gravitomagnetic coupling, and we have another spin force coupling appearing over here. And then we have our tidal and rotational tidal deformations. And these have as coefficients, well, this 1, that's the coefficient for the quadrupole tide. And then we have the response, which is this decaying part. So we have these 4 orange love numbers then appear in the metric. Okay, so then we can go ahead and use that procedure to compute some love numbers. Well, this part is completely well known. I'm computing polytropic love numbers, well, in the gravitoelectric and gravitomagnetic sectors. And, well, so there's different polytropes. We checked certain limiting cases because we wanted to make sure, since we were finding these results that were kind of in conflict with other people, we wanted to make sure we had all the correct limits. So I'm plotting here the love number against the compactness of the star, and the 0 compactness limit is the Newtonian limit. So we computed these in Newtonian theory, or post-Newtonian theory, when we had the spin. And so fortunately, we do hit all these limits. And also, we computed these love numbers for an incompressible fluid, and then we see that as the parameter n becomes smaller, we approach the incompressible fluid limit. So we have the gravitoelectric tidal love number, the gravitomagnetic tidal love number, and yeah, these consistency checks. Now, this is the gravitoelectric rotational tidal love number, and the gravitomagnetic rotational tidal love number. And again, we find that they're consistent with their limits.
Sorry, may I ask you a question?
Yeah.
The fact that they all decay with compactness, is there a simple explanation?
I think the simple explanation is just that as compactness increases, that you're approaching the love numbers of a black hole, and the black hole is supposed to have 0 love numbers. I think that's all there is. And I'm not sure about the physical significance of saying the black hole has 0 love numbers. I mean, I've never really understood if that's just a kind of a matter of definition, or if that makes sense as a result. But yeah, the point is they all go to 0 here because that's the black hole limit. Okay. So now, moving on to the realistic equations of state, people have tabulated all these equations of state based on some kinds of nuclear physics simulations and very complicated things. But you can approximate them often by just taking a piecewise polytrope. So you have these different ranges of density, and you just have polytrope for different ranges. So we're going to take this 3-part piecewise polytrope for the interior of the star, and the crust will take it to be a piecewise polytropic approximation to this SLY equation of state, which people are more confident actually describes the crust because it's a lower density where we have better handle on it. And we're also going to restrict to equations of state that admit 2 solar mass neutron stars, because we believe there are 2 solar mass neutron stars, and that do not admit superluminal sound propagation. So then, from the study that I'm referring to, this leaves 7 equations of state that we're going to look at. And we're also going to plot them over compactness ranges such that the masses of the stars are at least 1 solar mass, and they're stable by this turning point criterion.
Can I make a comment
Yeah.
on what Luciana just said?
Yes.
So earlier, you ignored the rotation on the grounds that really the perturbation that the perturbation that produces a rotating black hole is indistinguishable from rotation. It's not that they really ignored it, it's just that it's indistinguishable from
So you mean we're just kind of renormalizing the rotation?
Yeah.
Yeah, that kind of...
So that's number one.
Sorry,
Number two, you've also removed the perturbations of the star. So you've removed, for example, the quasi-normal fluctuations of the black hole. So basically, you've removed those.
Yes,
Yeah,
but
no.
I can understand that if you have a single object. In a binary system,
Sorry.
you no longer have this conformal thing.
Yeah, I think the rotation thing, I think I misspoke. It's not that it's like a spin. It's not like a continuously rotating thing. It's just an overall, just a single rotation. I mean, it's like it's a rigid rotation.
Which is spherically symmetric.
Yes,
I mean,
yeah.
it's a rotation.
Yeah, but it's
not
not.
symmetric, right? I mean, the tidal deformation is intrinsically non-axisymmetric.
Yes.
You know, I am here and the other one is there. It's not
Yes,
axisymmetric.
in GRO you can have a deformation which is purely axisymmetric.
Yeah, that is fine and understand. It is if you know, in a binary system you have an m equal 2 and not an m equal 0 perturbation. And that's what I have problems with.
Sorry, what?
So, you know, this kind of refactoring out the quadrupole. I understand if you have an m equals 0 overall symmetry, then you can say, okay, I'm just renormalizing everything because I know I have axis symmetry. But in a binary system, you have an m equal 2 underlying symmetry.
Mm-hmm.
And then I find, you know, in fact, the tidal deformability, you know, these objects are not quadrupoles. They are more like olives, to be, you know, a bit pragmatic. And olives are not axisymmetric, at least not on the right axis.
Yeah. I think it's. I said at one point that it's like renormalizing the spin, but I don't think that's actually right. It's not that it's like an adjustment to the spin. Just to clarify that, it's just like a fixed rotation that happened.
Okay.
So it's not the same. I think that, I mean, I could check the paper, but I think that's what it is. And yeah, I mean, well, we can talk more about that one afterwards, I guess. But anyway, right. So where was I? Yeah. So I mean, these are just a bunch of equations of states that we're going to consider, and we can work out our tidal love numbers. And well, as you can see, I mean, here's 7 of them. We've also plotted our polytropic love numbers on these figures, and well, they're just some curves. These dotted ones or these dashed ones are supposed to be these slightly more exotic equations of state, and well, in some of these figures, they seem to have similar behavior because they're slightly more exotic. But I mean, the point is all that you get different love numbers depending on your equation of state, and I'm not reading too much directly into these figures. We can do a similar analysis for the rotational-tidal love numbers, work those out. Okay. Now, when it comes to the universal relations, what we're doing is just following this approach that Yagi and Yunus had to try to fit to try to do these fits. So what they did is they just did these log-log polynomial fits between the moment of inertia, or this rescaled moment of inertia, and each of the love numbers, and evaluated the percent error. So these are well-known I-love relations that I had on, well, I had one of them on the first slide, or one of the early slides. We're just verifying that they continue to hold. So here's I versus KL, which you get this nice curve that holds, within like 0.5% for these equations of state. And here we have I versus K mag. And that holds within about 1%, I guess. So you get a little bit of the degradation of the universal relation when you go to the one involving K2 mag. But it still holds, reasonably well. Now we have also these. Now these are new. These are these rotational-tidal extended I-love relations, and we find that they also hold quite well. So this is the relation between I and the and FO, which is the octopole generated by the gravitoelectric quadrupole coupled to the spin. And we again get this, this universal relation for all these equations of state to within about 1.5%. And similarly for the KO, which is the gravitomagnetic sector, that's within, say, 1 to 2%. And I mean, so the universality continues to hold, but slightly weaker. But then we realized, well, if you have relations between the moment of inertia and all the love numbers, you ought to have relations between all of the love numbers themselves. So we checked these love-love relations, and they also hold. So here's K mag and KL. They hold at the 1% level. You have FO and KL hold with the 2% level. And
all you need is love.
yeah, okay. Yeah, we should have called the paper that maybe. But yeah, and then, well, they continue to hold. So here, this is K2L versus KO. That's at the 5% level, and FO and K2 mag at the 0.5. And then the last pair also holds at the 2% level or so. So it doesn't actually degrade that much when you go to these higher order love numbers. Like I was thinking it would start to break down more visibly, but it seems to work, reasonably well. Now, I think just take this as further evidence that, a single quantity seems to describe all the tidal and rotational tidal deformabilities, the moment of inertia, and the spin-induced quadrupole, as long as you're restricted to neutron stars. I don't know why it's different when you go over to quark stars, but for all of, at least for this class of equations of state, that's all you need to measure. It's really just one more quantity in addition to the spin and the mass that you can try to measure for the neutron star. So now I just wanted to mention this before. I mean, to compare to previous work, Pani, Gualtieri, and Ferrari found deviations from this universality of up to 200%. So this is why we did all our consistency checks. And I mean, they had a slightly different model for the fluid. They didn't have this irrotational state assumption. They had a static assumption. But in the limit in this zero compactness limit, both our result and their result should limit, for this love number where there was a discrepancy, this FO, should limit to the Newtonian limit. And you can see our curve is this black one that goes nicely to the Newtonian limit, and theirs is this dashed red curve, which is nowhere near it. So we're pretty convinced that our results are correct because we did all these checks, and also that we're finding this universality, which is non-trivial if you make a mistake to get it. Okay, so that was just that. So like I said, I mean, I talked about this before, like the utility of having these universal relations. I mean, we have the idea is we have these three Hare relations. So now you can fully describe a neutron star exterior by the mass, the spin, and the one new quantity. And I mean, this is relevant during the inspiral. Obviously, after the merger, and you get all kinds of messy stuff coming out, you're going to have more parameters to describe. But I mean, and the uses, like I said, are to break degeneracies in the gravitational wave observations. For example, there's a degeneracy between the spin-spin and the rotational quadrupole in the phasing at the same p-n order. But if we, you can break that because you can compute this rotational quadrupole in terms of the love number. So that allows you to break these degeneracies. We can test general relativity because if we could measure these quantities independently and find that they don't lie on that curve, then there's something wrong with our underlying model. And also we can improve parameter estimation if we can rewrite some of our quantities in terms of other ones. But the reason for universality is not really well known. Some people have done some work saying that as you move to higher compactness, there's some sort of self-similarity of isodensity contours within the neutron stars in the case where you have this universality holding. So it could be related to these things, but it's not really settled at this point. Whoops. Oops. Okay. Okay. Now before I finished, I just wanted to talk about some other work that appeared kind of filling in some of the missing stuff that we needed, which is, and it just came out like last week or so, which is the effect of these rotational-tidal love numbers on the waveform. So the idea to do these calculations of how it affects the waveform is you suppose that you have a quasi-circular orbit in the post-Newtonian expansion, and then you see how that's corrected by these rotational-tidal effects. You can set up some Lagrangian framework in which you can do this, and you see how some of the energy is transferred into these different modes. And so that gives you a slightly different circular orbit, and then given those circular orbits, you can compute the energy flux from gravitational radiation using this quadrupole formula. So these are just the changing multipole moments of the system. And then, since that energy is lost, it then results in the change to the gravitational wave phase. So this is this basic argument of Flanagan and Hinderer. But now, this is a new result that was done separately by these two groups. And so this is the waveform phase, and it's the psi is the phase as a function of frequency. And we see, well, this first two lines here in this phasing, well, that just corresponds to point particle effects. But then the leading correction due to tides is at 5 pn, and this is just proportional to K2L. This was known since Flanagan and Hinderer. There's an effect of the gravitomagnetic quadrupole that comes in at 6 pn, and the final effect, this new effect, is this rotational-tidal love number effect, and that comes at 6.5 pn in the phasing. So that arises. What's interesting is it comes in at the same order for FO and KO. They both come in the same order. But then also, there's two other love numbers that we didn't address in this talk, which are the quadrupoles that are induced by octupole applied tides coupling to the spin. So those also come in. These are the FQ and the KQ. These also come in that order. Now, there's an argument that, in fact, these have to be very closely related to these other ones, but that hasn't totally been sorted out yet. But the point of all of these universal relations is that all of these corrections that we're finding here are dependent on each other. They're not independent, and if you know one, then you know all of them, and you can just, if you can measure these different PN orders, you can then make sure they follow the correct relationship. And in addition to getting your tidal parameters, you get to test your general relativity theory, or your entire framework, basically. So that's basically it. So to conclude, we calculated the rotational-tidal love numbers for realistic slowly rotating neutron stars, and we extended this universality. And really only one of these love numbers is independent, and all the other ones depend on it. So yeah, going forward, I think we want to incorporate these new quadrupole rotational-tidal love numbers into the universality relations, and yeah, try to understand where this universality comes from, which is really not clear. Thank you.
Yes, thank you very much for interesting talk. So are there any questions or comments? Yes, please.
So can you go back to your, where you show again the universal relations? I mean, it's my understanding that you need to set a spin here. Size for the spin, because these are spinning objects.
Yeah, you do, but the love numbers themselves don't depend on the spin. So you would have the love number. I mean, the response would be the love number times the spin times the tidal thing. So
you just read off the coefficient.
Yeah, you just read off the coefficient. But I mean, there are a lot of markers here for each. Even for each equation of state, and that corresponds to different mass stars at each equation state. But yeah.
Okay. And if I may, another question.
Yeah.
These might be hyperfine, but the neutron stars, besides having spin, they also have a magnetic field, and this will change
Yeah.
the response to a tidal field. You know, if you have a magnetic field, you have a magnetic tension, which will oppose to that.
Yeah, I mean,
And
that's a,
it's been shown actually that universal relations are broken
uh-huh.
if you have a strong enough magnetic field. It's very easy to imagine. So, and it doesn't need to be a huge magnetic field. That Gauss already does it. So, are you going to consider magnetic field induced deformability?
Yeah, I mean, I'm not familiar with that particular work showing that the universal relations don't hold, but I mean, you couldn't, in principle, try to extend this stuff to include a magnetic field. I mean, like you said, it's a strong magnetic field. I don't know how to treat that perturbatively then, but okay, yeah. I mean, it would be interesting to see, try to extend it. Presumably, you would get corrections due to couplings between all these various fields.
It's going to be awful, but
Yeah, I mean, this is horrible enough as it is. I mean, like most of this framework, I'm fairly new to this whole thing with these neutron stars, and most of this framework was already developed. And trying to read these papers was a bit of a mess. But yeah.
Okay, please. Okay, could you go back to the first slide with this potential and log number? There is a potential, it is the deform potential.
The potentials?
Potential.
Back more?
Was the first one which
Like this? These are
no.
These are what I call potentials. More?
Oh, yeah.
That? No?
The first one.
Oh, at the beginning?
Yeah.
Oh, the Newtonian potential.
Yeah, Newtonian
Yeah, okay, I'm almost there. Here.
Newtonian potential.
Yeah.
The log number is here.
Yes.
Okay. This is the definition the log number of this in this case, yeah?
Yeah, this is definition of the love number, yeah.
If you have a relativistic potential coming from
Yes.
Sparty solution, for example,
Yes.
inside Sparty solution, you have a similar definition.
Yeah. So so remember this equation, but the closest related one would be if I go forward. This. So the GTT component is closely related to the Newtonian potential. So we have the Newtonian potential here, and then we have the 1 plus K2L times R 1 over R to the 5 times the applied field. So that is the Newtonian one in the relativistic version. But then we have these new ones also.
Yes, but if you have a relativistic vector,
Yeah.
you have a metric.
Yeah.
This metric is a linearized subspartic solution or full spartic solution.
It's so it's linear in EAB, and it's linear in BAB, and it's also, well, and then you have to go to second order in perturbation theory to compute the crossed spin tidal terms here. But
And distribution of matter is included here.
This would, I mean, well, this particular metric that I'm writing down is outside the matter, but you do have to solve the Einstein. You're solving the Einstein equation inside the star and outside the star, first at linear order and then at second order, to compute all this stuff. Yes.
Thank you.
Yeah.
Okay, thank you. Yes, please.
If you do not understand these universality relations, how can you use them to test their relativity?
Well, you use it. Well, it's a good. I mean, I understand your issue, but at least they hold. We know they hold to this percent level when we look at the equations of state that we consider reasonable. So, I mean, it's not a perfect test, but I think it's still very useful because it would tell you. I mean, it tells you either there's something wrong with general relativity or with how you're treating the star. Because, I mean, the equation of state either has to be completely off from the ones that we've considered so far.
The universal relation.
Well, the universal relation we know holds for the equations of the state we studied, right? Well, that's a calculation that we've done. And that holds for the for the ones who
you
study.
don't understand them, so maybe there's some.
It's empirical. It's empirical. I agree. But I mean, it'd be better if we could get a better understanding. Absolutely. Yeah.
Okay. Yes.
Yeah.
Please.
Okay, at one of the first slides you just showed that there is different relation for neutron stars and for quark stars.
Yeah,
And I
that's
guess that for quark stars you have just quark stars without crust. So the equation of state is very stiff and this is very difficult to deform the star. But is somebody who just check if you add a crust of nuclear matter, if the relation would be not identical like for neutron stars?
I mean, that's
Do you know any?
I don't know.
calculation?
I don't
Because
know
it
of
is
anybody
not
who did
so-
that calculation.
Okay.
But
Because according to me, it could be like that when you just
Yeah.
get a crust,
Yeah.
the crust is just built of nuclear matter, normal one, quite soft, and you can deform this quite easily.
Right. But I mean, they still get a relation for the quark stars. But
I know that
yeah.
for quark stars,
yeah.
but bare quark stars, yes, without crust.
Yeah.
So in this way, you have the gamma value.
Yeah.
The adiabatic index going to infinity at the surface, you have high density jump, but this is similar situation when you just perform calculation of the inspiralling neutron stars and quark stars. You can also see that there are quite different lines looking at the marginally stable orbit.
Mhm.
But when you add a crust, the situation changes.
Yeah.
So this is maybe you
That-
don't have such kind of division because in reality quark stars should have a crust. You have a matter, you know.
That could be it. I don't think they believe though that the universal relation is related to the crust of the neutron star, because that seems like an obvious guess because we give them all the same crust. But if I remember right, they claim that the universal relation is related to like the middle or the 50% to 90% of the radius or something, not the crust. But I couldn't say much more than that.
Okay. So thank you very much, and let's thank the speaker again.
Thanks.